How do we go through an approach? All we need to do is convert the name into the symbols. Lithium symbol is Li. Sulfide, it's just S. A couple things to remember here. That D, officially the IDE ending, doesn't show up on any of our elements. Okay? That's referencing an element that is now changed to an anion. Okay? So we're changing its structure, we're putting it in a compound. So it's a negatively charged species. There are a variety of endings that we could drop on there. We've got IDE, what else? ATE and ITE. How do you know you're specifically looking at an element and not, say, a complex ion? But there's an I and an E in both the others, so I don't know, I accept the D. Look for the D. If you see that D there, you're then going to be pulling out, in most cases, knock it off. In most cases, you're looking at an element. There are a couple exceptions to that. One of those exceptions I've already told you to memorize. What complex ion ends in IDE? You all spent the time to memorize. Chloride is not a complex ion. That is the element, just Cl. Cyanide, way to pick the one I told you to not memorize, but that works. Cyanide. Oh, it does have a star on it? Oh, okay, well I lied. Cyanide it is. That is a complex ion, cyanide, with the IDE ending. So it's kind of a bit misleading there to just say recognizing the D gives us the element. Okay. What's the other one? Much more important. You'll see everywhere. Hydroxide. Okay. Again, with the IDE ending. Both of those are complex ions that end with that DE ending. Any other time you see that show up, you're looking at an element. Okay, most cases. Okay, so now, back to our compound. We came up with lithium and we came up with sulfur. Is this the correct formula for lithium sulfide? No. Okay, good. How do we know that? We have to look at balancing the charge on our individual elements. So how do we know what the charge is on lithium and or sulfide? They're ones that you have to have memorized. The lithium has a +1 charge. The sulfur has, or sulfide, has a -2. If we put them together as a 1-to-1 ratio, 1 lithium and 1 sulfur, or sulfide, what would our charge be? -1. Because when we add those two up, we'd end up with an excess of negative charge. We need to make sure that when we put the compound together that the charge comes out to be 0. It must be neutral. Okay. So we need another lithium. So we could go through and write it as this is our formula. LiSLi. Okay, why not? That holds all of our element pieces in it. But what happens if we had to add 4 or 5 of an individual element? Our name's going to become really obnoxiously long. So we want to condense. How can we condense? Make a subscript right after the element you want to multiply. And we now have our proper formula for lithium sulfide. Good? I think I'll take that sure as an affirmative. Magnesium sulfate. Symbol. Mg. Okay. If we said S, then we're looking at sulfur all by itself, which would mean when it comes in as a compound, it would become sulfide with the D, just like we saw in the previous question. There is no D there. We're not looking at sulfur by itself. We are necessarily looking at a complex ion. What's the formula for that complex ion? SO4. How did you know that? It's one you have to have memorized. Okay? The Tutoring Center offers a nomenclature workshop on this Friday. You can go and attend, and they give you some mnemonic devices to help you memorize those. Okay? What the charges are and how many oxygens and all of that nonsense. Okay? To me, it's the exact same thing as just spending the effort to memorize it. Okay? So up to you to decide which you prefer. If you want some weird mnemonic device, by all means, pay attention to the Tutoring Center. They will help you out. Otherwise, you just have to have it straight up memorized. So sulfate is SO4. Okay? Just like we did with the lithium sulfide, we need to now balance our formula and make sure that when we put these elements together, it is overall neutral. Okay, what is our formula going to be, or is it overall neutral? What is the charge on Mg? +2. Charge on sulfate? -2. When we put this together, charge balances. Formula is perfect as is. Write it MgSO4. We're done. Yes? They won't both be positive, or at least the only way they would both be positive is because you were naming a compound wrong.
So you can never put two positive elements together and make something?
According to the nomenclature system that we are working with within the limits of this class, yes, that is true. Okay? Last one, or questions still on that one? Okay, how about the last one? There was an 08. What's the 08?
I just said, why is it 04? Is that just because the 8?
What is the symbol for sulfur?
S.
Why? Because we've defined it to be S.
Okay.
Same thing is happening. No, it's the same thing is happening here. Why is it 04? Because sulfate is SO4.
Basically because we're supposed to.
It's the name of the compound. If we went through and said Si, okay, well, that's not sulfur anymore. Why is the I there? Because we're trying to represent a different element. Same thing's happening with our sulfate being SO4.
Sulfate is a compound. It's not sulfur.
Sulfate is not just sulfur. It is a compound. Okay? It's combined of sulfur and oxygen in a particular relatively stable format that we then name as an independent species, okay? Known as our complex ions. Not to be confused, since you brought it up, with sulfite, which is SO3. Okay, what happened? We've changed the number of oxygens, so now we change the name. Okay? You are responsible for tying those names to those proper symbol notations.
Can you explain the positive 2 and the negative 2?
So the positive 2 and the negative 2, the explanation of them we are getting to at this stage, stick with memorization. Okay?
So we should
Tidbits to get you through this. What was the charge on lithium? Lithium? Lithium was a +1. Find lithium on the periodic table for me. Which column is it in? The first column. Where's magnesium? Second column. What was its charge? +2. Okay. So there are some helpful kind of memorization techniques within the periodic table for some organization. We have to be careful and over-relying on that. We'll explain where those are coming from once we understand what makes the charge. Okay. What did we say made the charge? The number of electrons balanced against the number of protons. Okay. So we have to understand something about where our electrons exist and how they can exist. That will help us understand the charge. At this stage, all we've talked about is our nuclear notation, protons and neutrons, and that electrons exist somewhere. Okay. The next part is where do those electrons exist? Okay. I want you started on nomenclature before we talk about that because nomenclature takes a lot of time and effort to practice. So as you start to do it, you'll start to memorize certain charges. That'll help you out that when we hear the little loopholes on how you can get them memorized without memorizing them per se, you can do better at it. Okay? Last one. Symbol for cobalt. Symbol for chlorate. If it was just Cl, it would be chloride. You'd have that D in there. We don't. So with that T, we're looking at a complex ion. We'd have to know what that ties back to. There were a bunch of people dropping them out there. ClO is partially right. 3. Wow. Good chorus. Good job. Yes, chlorate is ClO3. Okay. Is our formula balanced? Figure out if our formula is balanced. If we've balanced out our charges, we need to know what the charges are. Okay? So let's start with what I would argue to be sort of the easier one, chlorate. What is the charge on chlorate? It is -1, and you know that because it's one of the ones you'd kind of have to have memorized, unfortunately. Okay. Charge on cobalt. Okay. It's not one you're required to memorize. How did you know it was 3? I told you what it was. That's what the Roman numerals mean. The Roman numerals tell you what the charge is. Those of you wondering, wow, how did she figure that out? Did you watch the video? Interesting. The video that explained what the Roman numerals meant tells you what they mean. Go figure. So our charge on our cobalt is a +3. Would our formula balance? Okay. We have a +3 and a -1. If we just had one cobalt and one chlorate, what would our charge be? A +2. Okay. So what do we need to balance out the charge? Right now we have an excess of +3, right, or a +2. So we have too much positive charge, so what can we do? Add more chlorates. Now what would our charge be? +1. We're still not there, so what do we need to do? Add another one. And now our charge would be +3 and -3, which gets us a neutral charge. So we now have the proper number of them. That's an awful lot of writing, so we can condense that by saying, way to just jump with the parentheses. Okay. Why would we need to include parentheses?
Then it would look like you have 33 chlorate.
If we don't include the parentheses, it looks like COClO33. It's not ClO33. It's 3 chlorates. So what we would do is include that 3, and now the parentheses being directly in front, the 3 applies to whatever is directly in front of it, whatever's in the parentheses. Okay? Questions about that? Some things I want to go through and note. You'll notice that we had a lot of work shown on this. +2, we even had all those CLs. Whoops, ClO3, ClO3. We started with a +1 that became, or that's a -1. A -1 that became a minus, frick, add up. No, I did that right, -1 that we then said became a -2 by adding a second chlorate. We then said became a -3 when we added that third one. So that's an awful lot of work. If you showed that on any of my tests, I would probably give you credit for it. Because you've shown me the work, I understand what you're trying to process and get through. But if you're asked just to provide the formula, someone looking at that might be, well, what's the formula? So what we can do is simplify all of our work down to become so we're removing the spaces, we're just condensing it into a neater format. Make sense? Okay. Questions on that? Okay. Just to give you an idea of what might be happening, say, on Thursday, you might be asked to do the next sequence. Pick another random 3. Yes?
Question about like where it says cobalt-3 chlorate.
Mm-hmm.
How would we put that from the actual, where it has the, where, I don't know how to say it. Where it has CO and then parentheses ClO3, parentheses 3. How do we get that to the name?
How do we go from the formula to the name?
Because we don't know, how would we know if it's 3 cobalt?
Is it 3 cobalts?
Well, that's what the name says. That's what
No. What did the Roman numeral say? The charge, not the amount. Look at the formula. The formula says there is 1 cobalt. So you're right. How do you do the reverse going back to the name? That is a good question. Since you've picked 3 names to formulas, maybe on Thursday I'll make you go formula to name, and we can approach that question then. Okay. Remember, your Roman numeral only applies to the charge. So how would you back calculate from your formula back to the name and still account for that appropriately? It's a good question. Okay. So periodic table. We're now going to jump into chapter 5. So the way I look at chapter 4 and 5 is the first half of 4 kind of sets us up with our nucleus. Second half of chapter 4 talks about electrons. Well, the first half of chapter 5 really gets us patterns of what's going on with our nucleus. Okay? So I like to split it up where we talk about our nuclear stuff first, and then our other nuclear stuff, then our electrons, and then our electrons. So it kind of sets up a better pattern between them, in my opinion. So once we've now started to build our atoms, okay, with our nuclei, we can now start to look at classification of the elements. How do we organize these into some fashion that we can then interpret relatively quickly? Okay. Remember that this is old stuff. 1829, we get our first chemist that is starting to group some of the elements together and notices that they come up in groups of 3. Okay. And what he noticed within those triads was that those 3 elements all exhibited similar properties, okay, and had very predictable patterns within them. So if we look at the periodic table, some of the groups that he might have come up with would be, say, lithium, sodium, and potassium. Symbol for lithium was Li, symbol for sodium. Na, symbol for potassium. K. If we look at the periodic table, where are those 3 elements? All in the same column. Okay. You'll notice that he didn't include, say, rubidium or cesium in that. Why not? It has to do with the order of discovery. The smaller our elements, the easier it was to discover in most cases. The larger the elements, the harder it was to discover, which means if we can't discover everything, say, underneath nickel, it's hard to predict other triads. So his initial discoveries were based off of what he had access to. And if he only has access to the upper third or the upper half of the periodic table, we see groups of 3, okay, within an individual column. A little bit later, we had Newlands, went through and looked at the 62 known elements. So here we're actually quantifying how many elements they had. 62. Okay? 1829, we had a few less than 62. And if we even deal with 62 on our periodic table, that doesn't get us super far into it. Okay? His theory went through and he noticed some patterns based off groups of 7. Okay? So by groups of 7, he grouped the first column, all of those elements together. There's one group. Then he had the second group. His third group. Actually jumps kind of across the periodic table. Fourth group, fifth group, sixth group, and seventh group. Interesting. In roughly 7 groupings and roughly 7 columns-ish. Yes, we are ignoring the middle for the moment. Okay. He called this according to the law of octaves. I'm no music major, and someone that was a music major explained to me that octave does work at 7 because it repeats every 8th. Yeah. Is I guess what it is for your octaves. Okay, and so that's what he's referring to here. Every 8th we get a repeat. Okay. A little while later, we end up with Mendeleev. Okay. Mendeleev gets a lot of the credit for our final periodic table assumption, our composition, not so much for the organization, but for the predictive ability. So we ordered all of the elements that we had access to according to their atomic mass. Okay? Why the atomic mass and say not the atomic charge? Why not the atomic number? No, the atomic number, so our nuclear charge, sorry, you're correct in saying that. Why not go based off of our atomic number instead of the atomic mass? What was the atomic number? Protons and neutrons. When did we know protons and neutrons? 1900s. This is happening late 1800s, 1870, 1880. We don't understand what goes into a nucleus. We just have these individual elements. So we don't have a nuclear charge. What we do have is an atomic mass. We can determine the mass of each of these elements. Okay, so we organize it based off of mass. It gets really, really close to the actual periodic table. So if you go through and compare, it matches almost perfectly. There's a few cases where it doesn't match to our real one. Okay, but for the most part, it matches. The big thing that's important within this is if you look in the middle here, we've got these things that he's labeled as ekas. Okay. Those ekas didn't exist. So when he put together the periodic table, he noticed that between aluminum and yttrium, that there was a big gap in the physical properties. There had to have been something missing there. So he said, well, I think there's two somethings. And those two somethings have these properties. Right? So he predicted, based off of his table, what we would expect out of it. How should they react with oxygen? What should their mass be? Okay? He could come up with some pretty amazing predictions from this. Okay? And in some cases he was right, and that's usually what he gets credit for. In other cases, he was wrong, and we kind of swept that under the curb. Okay? But the predictive ability was the best part of this. Okay? After we went through and dealt with this, wait a sec. There we go. Whoop, not that one. Other one. Stop looking at what I'm saying. Don't look at the man behind the curtain. Okay. Oh, shoot, no. I had it erased the other way around. I had it right the first time. Ecosilicon. So these were his predictions for this element, okay, which was later discovered and named germanium. So he went through and said, you know what? It's going to be gray. That's a real big stretch. Most of our elements are gray, silver in color. So don't give him a lot of credit for that one. How about the atomic mass? Yeah. He said the atomic mass was 72. So we got gray. The atomic mass is actually 72.6. This is just based off of looking at trends within the table. Said that's what it should be. Density. He guessed 5.5, came out to be 5.32. Okay. This is just, again, looking at the properties of all the other things around it and just saying, what should it be? That predictive power is ultimately why we name things after people, because they were actually able to predict the future, sort of. Okay. As we continue to go through, you'll notice that his approximations are pretty darn close to the actual results. Okay. This is before we even knew they existed. Look at the time difference. 69 versus 86. Okay. These aren't just guesses. Okay. We could just say, well, it's a random number, here it is, here's a guess. That might work for one. But to go through and predict that many possible factors, this isn't just a guess. This is using the organization of his periodic table to predict these things. Incredibly powerful. Yeah.
Do people still use like the periodic table today to predict
what we could potentially get? Yeah. So we'll keep trying to go through and build ones. We start to run into other issues. But yeah, we can start to predict potential properties for those. Okay. Last thing before we kind of move into our official periodic table, where's our year? 1913, we get our nuclear charge. Okay. That was Moseley with the protons and neutrons. And that's when they went through and said, oh, actually, the atomic mass doesn't perfectly line up. We actually are going to organize based off of the atomic number, the number of protons in the nucleus. Okay. That's where our periodic table now lies. And if you go through and compare mass versus number, there's only a few cases where Mendeleev's table didn't quite work because the mass doesn't match up. Okay. Most cases it worked out pretty well. The other big discovery that happened in this in 1894, we end up with helium, neon, krypton, xenon, and radon. Okay. That's the very beginning of this. Those are typically labeled the inert noble gases. Why would it take so long to discover those compounds? So gases makes it more difficult, but we kind of found oxygen. It has to do with their reactivity. Inert means they don't react. Most of our periodic table is built off of how those elements react with other elements. And we can start to make approximations based off of that reactivity. These species don't react with other elements, which makes them a lot more difficult to track down and find. Okay? Once we had them, that helped with our final organization, looking at our atomic numbers. Okay? And that gives us our last column on our periodic table. Okay? So, periodic table, organized according to atomic number. Okay? What we will then add to this in a little while, once we understand where our electrons are, is we can get an idea of how it's organized according to our electron orbitals, or where our electrons exist. Because the periodic table embeds a lot of that information. Okay? Some groups and periods that can come out of this, some names. We just want to associate things with this. Okay? You'll notice that I already don't like nomenclature, so coming up with names for columns in the periodic table I'm not the greatest with either. Okay? But some of them you are more responsible for than others. Okay? The two that I notoriously get backwards, alkali metals and the alkaline earth. Okay? Kind of irritating when we name things similar to each other. It makes it difficult to remember which one's which. Okay? You need to try and remember those. Your alkali metals are your first column, your alkaline earth are anything in that second column. Okay? The next big name that's on here, kind of not showing up nicely, is our transition elements. That's that entire middle section of our periodic table. Those are our transition elements. Okay, so we don't name individual columns within it, we name that whole group. After that, we'll jump over to our last two columns that you're ultimately responsible for, halogens and our noble gases. The noble gases we just mentioned are helium, neon, argon, krypton. Okay? Those don't react with things, and those are going to become important when we look at our electron configurations. The halogens are the one right next to them. Okay? Those are the primary 5, if I counted right, that I would want you to have memorized and nailed down. We do have some others. We have the inner transition elements, okay, which you might hear reference to. Don't stress too much about those. Any ideas why? What do you mean they're not up there? They're on the periodic table.
No, they're not. They're like kind of disattached things.
Okay, so we floated them out of the main periodic table. The other reason we did that is we could have inserted it, but then our table just becomes incredibly long as opposed to kind of box-like. Okay? So those do sit right inside the transition metals. Okay, but we get another kind of jump like we get with the transition metals.
They're just more rare.
So they're more rare, that's one option. So if they're rare, what's the likelihood you're going to work with them? Not very often, which likely then means why should we bother talking about them? It's a little bit of gray area there, but it's pretty close. They also tend to be, what was that? Radioactive. What do we know about radioactivity? Yeah, it's dangerous. What are the odds we're going to give you something dangerous to play with? Relatively, on the grand scale of things, we don't give you super dangerous things to work with. Okay? Because we don't want you dead. Okay? We want you to live and actually work with these things. So we tend to not look at them as frequently. In this class, we pretty much ignore them. Okay? There are 2 more columns that I like to go through and name. Okay? And the only reason I like to name them is just because I think they're fun to name. Okay? Everything underneath nitrogen and everything underneath oxygen, those 2 extra columns, I think are just fun. Okay, so let's try this first. How about you try and say the family name for the nitrogens?
Nictogens.
Oh, that's pretty good, yeah. Nictogens. See, it's kind of fun to say. You want to try and say it? 3, 2, 1. Yeah, it's kind of cool, isn't it? The other one for oxygen? Chalcogens. Yeah, also sounds kind of fun to say. Okay, you might see those float around. Every so often I see those pop up. I'm like, what is that? Oh, yeah, that's kind of a cool name to give it. Okay, you're not responsible for those. Okay. So back to our periodic trends. I thought this slide was a lot earlier. So let's take a look at our periodic table here. So we've got sodium. That's not sodium to start with. That's lithium followed by sodium followed by... That's a good question. Why does that say francium? Oh, well, yeah, we'll come back to francium. What can we predict about? What's in that gray box? Potassium, followed by rubidium, followed by cesium. Okay? So we now have this massive table of data. Okay? And this is ultimately what Mendeleev was looking at. Okay? So let's say potassium was not discovered. We want to come up with some prediction for what those values might be. Okay. To do that prediction, what are we going to do? Look at the trend for everything else within that column and try and come up with a guess for it. Okay? So the question at the bottom actually says, what's a reasonable density for potassium given this data? Okay? Let's scale that up. Give me a reasonable guess for every single one of those four things. Okay? If you got to talk to people, talk to people. Spend a minute.
Bigger.
It's getting bigger. Okay? So as we look from lithium to sodium for our atomic radius, we go from 0.152 to 0.186. So we would expect it to get bigger. Okay? The guess made was taking the difference between 0.248 and 0.186 and splitting that difference to get us the 0.217. Okay? It's not a bad guess. We could also go through and see how much it changes from lithium to sodium. What's our change there? Roughly 0.03. To go from rubidium to cesium, 0.15. So our differences are getting smaller maybe as we go down. So maybe adding maybe 0.2 to our 0.186 would be okay. And that still gets us pretty darn close to that 0.217, right? What about for the density? How do we calculate the density?
Same way.
Same idea. How about the melting point? Roughly the same idea. We're dropping each time. What happened with our atomic mass?
I have no idea.
Okay, so what we need to do is think carefully about the numbers we choose. It doesn't matter what number you pick, but reason through it. If we said 15, what's happening to the atomic mass as we go from lithium to sodium? It's getting bigger. What's happening to the atomic mass as we go from rubidium to cesium? It's getting bigger. What would we expect to happen to our atomic mass as we go from potassium to rubidium? It's get bigger. Oh, everything's matching, right? What would we expect to happen to our atomic mass as we go from sodium to potassium? It should get bigger to match the trend. Is the guess getting bigger? No. Does that mean that number is a good guess? No. That's the reasoning that Mendeleev used to go through and approach these things. So what would be a better guess? I heard a lot of numbers. I think I heard 59.4. 39? Okay. We'll switch it to 39. You didn't just read the periodic table, did you? Okay. Thank you. Just checking. So, we've got the numbers. What are the results? We take a look at the atomic radius. What was our guess? We had 0.217, 0.227. Not a bad guess, guys. Good job. Atomic mass? 39.4, we said? That's, wow. Good job. How about the melting point? We said 59. Dang, pretty good job. Potassium? Oof. Okay. Did it match the trend? No. Does it have to match the trend? No. What we're using this is to predict. Just because our prediction is wrong doesn't mean the whole thing gets tossed out. It means something else is happening in that range. What is that something else? I don't know. It's what we should try and figure out. Maybe we'd go through and now study and explain why that density was so different. When it comes to the test, if these were your answer choices, what would be the best answer choice? If we guess A, what are you saying the answer is for A? You would say it does not match the trend. How do you know it doesn't match the trend? Because you looked at the answer. You don't have the answer. What I'm asking you to do is predict based off the data given. The data is 0.53 to 0.97 to 1.53 to 1.87. What happens to your density? It constantly goes up. So as a predictive ability, guessing it goes down is counter to all of your evidence. What's your best answer? B. Why not C? Because that's too high of a jump. That exceeded rubidium's density. Okay? It's not impossible to predict. It may be impossible to be right, but it is not impossible to predict. We have a predictive ability. We can see the trend happening within this. The trend is that the value goes up. The only reason that you would say A is because you know what the answer is.
What if you read the note at the bottom?
Yeah, it says it on the note right there. The density of potassium is slightly less than that of sodium.
Dang.
So if we're going to play this game, let's do that.
Well, you said, given the information, that's what.
Well, but given the information, you are also shown 0.86. So there's your information. That's what you have.
Okay.
Okay. The issue on why I picked potassium is what happened. It didn't follow the trend. Does that invalidate the trends that you saw everywhere else? Does that invalidate the trend between lithium and sodium? No. The idea is to be able to predict what is happening. Okay? Come up with an educated guess, not random shooting of numbers. Okay? If we look at what that says, read it really carefully. Small irregularities in group trends are not unusual. Okay. Why? What other things might contribute to those irregularities? When we're looking at density, what is density? Mass and volume. What contributes to mass? Weight won't quite sell it. We've talked about 3 different things that make atoms. What contributes to mass? The neutrons and protons. What contributes to volume? The electrons. So what we're looking at is a balance between the protons and our electrons. What's contributing to the mass? What's contributing to the volume? We will see irregularities because we haven't even discussed where the electrons exist. That might explain why we have an irregularity there. It could be based on other things as well. We still have to go based off of the trend that we see. Interpret the data given, not the data you want. Okay? That is science. And it turned out in our science experiment, were we right? 3 out of 4 times you were correct. We have a general trend. We can do some predictions from that. Okay. Interpret the data you have. When you find out more accurate data, you then have to adjust your theory. Do we have enough science understanding to explain why it's shifted? Not yet. Okay? Make sense? Predicting chemical properties, same general idea. Again, predict with the information you have. When we looked at our initial theory, we had elements grouped according to triads because those elements all reacted similarly. When we went through and moved into Mendeleev's table, we still had the same thing. Each of our columns get their own special name. Why do they get their name? Because they all react similarly. They have similar properties. So if we now go through and look at an individual family, lithium, when it reacts with oxygen, we need 2 lithiums to balance out the oxygen. What happens with sodium? We need 2. Where's lithium and sodium on our periodic table? Same family. Potassium. Same family and same formula. The same balancing act is happening. So within a column, we can predict, once we know one of their formulas, what other formulas with those same elements will be. So let's take a look at a possible exam question. The formula for the chloride of calcium is CaCl2. What is the formula for the chloride of barium? So what are we asking? Saying if I take barium and I take chloride, what numbers should I be associating with each of those elements? Should BA1 Cl2 or BaCl2? You can imply the 1. Why would you come up with that guess?
Because it's similar to the other one.
They're in the same column. We find calcium. It is direct, or not directly above, but above barium on our periodic table. Let's be annoying, because we already noticed that I'm good at that. So let's switch that up. Let's make this now the chloride of scandium, which is, I know it's one I didn't tell you to memorize. You might be able to guess. SC. Do we have data to allow us to do that analysis? We group according to the columns. In some cases, as we move from one column to the next, we can draw conclusions. But have we talked about that yet? No. Why not? We need a better understanding of why we can do that transition. Without that information, can we draw any conclusions? No. What would I need to do to change this question so we could guess the formula for scandium chloride?
What is the predicted formula?
Give us the formula of
That one.
I realized that was kind of mean. Yttrium chloride. Let's say yttrium chloride came out to be this. What would our formula for scandium chloride be?
CCl6.
We might predict now SCCl6 because our families are grouped. Come on, pen. Okay, does that make sense? One of the things that we'll notice is that when you look at your periodic table, trends through the middle of it kind of suck. Trends on the extremities, both the far left and the far right, work pretty well. But trends through the middle tend to be a little bit wishy-washy. Okay? Questions on predicting chemical properties? Okay? Periodic trends. Okay? Our periodic table has a ton of information in it. We have already looked at atomic number, okay? Atomic mass. We even have some chemical reactivity within our individual columns, okay, or our families. We can also draw trends about the size of atoms. So there's two big trends that you're kind of expected to memorize and work with. Atomic radius decreases as we go, up a group, which means as I go from iodine to fluorine, what happens to the atomic radius? It shrinks, it gets smaller. Atomic radius decreases as we go from left to right on the periodic table. So as I go from lithium to fluorine, what happened to the size? Took too long. As I go from chlorine to sodium, what happens to the size? I said you took too long, so I made it more difficult. It's going to increase. We're going the opposite direction of our trend. Okay? So let's guess at this. Why might that be the case? Let's look at the first one. Why might we expect the radius to decrease as we go up a column? Okay. You guys positive people or negative people? Positive. Okay, let's switch up our trend. Let's make the trend. As we go down the column, it gets bigger. So we become bigger as we go down a column. Why might it get bigger as we go down a column? What contributes to the size of our atom?
Electrons.
Don't move. I knew you were going to do that. Our electrons contribute to size. So this is an interesting dynamic on what that term size means. When we're referencing size, we are referencing the radius, which is ultimately the volume of the atom. One of the suggestions for size came out to be protons. Where are protons found? In the nucleus. How big is the nucleus relative to the atom?
Very small.
Very, very small. Remember, if we made the nucleus a marble, the atom is the superdome. So our protons aren't being tied to the word size as much as they're being tied to the word mass. Right? So when we think size, we need to be thinking volume. How much space does it occupy? Not the mass of the individual atom. Okay? So when we're looking at our periodic trend, as we go down that column from, say, hydrogen to francium, what happens to the number of electrons? It increases. Why did you say that?
Because everyone said it hates it, adds more valence.
Hydrogen has how many protons and neutrons? One. If I make a hydrogen atom, its charge needs to be 0. So how many electrons would it need to balance out that charge? 1. As I move to lithium, how many protons and neutrons does lithium have? 3. How many electrons would I need to have to make a lithium atom? 3. So as we go down the column, we're adding electrons. The more electrons we get, what would we expect to happen to the size? It gets bigger. Does that match our trend? Yeah, cool. We've got a quick way that we can have this rule memorized because it's all dependent on the electrons. We don't have to memorize anything. We just realize that as we go down a column, we add electrons. More electrons, bigger size. There's no rule to memorize. Where does it become tricky?
In the middle.
What happens as we go from lithium to fluorine? What happens to the number of electrons?
It increases.
It increases. Lithium had 3 electrons. A fluorine atom has 9 electrons to balance out the number of protons coming from our atomic number. So what would we expect to happen to the size as we go from left to right on the periodic table?
Increase.
It should increase. What happens to the size according to the trend? It decreases. Does this mean our initial theory is wrong? No. It just means we're missing some information about our electrons. Okay? That information is found back in chapter 4. Okay? So if we take a look at a graphic, so we go down a column, what happens to our size? Lithium to cesium, bigger. Beryllium to barium. Fluorine to iodine. All cases, it's getting bigger down a column. And that makes sense. We're adding electrons in. It should get bigger. But when we look left to right, we are also adding electrons. And yet somehow, our radius gets smaller. That is very odd. Okay? What that has to do with is where our electrons are existing. We talked about where protons exist. They exist in a super dense nucleus. And then we just said the electrons are just somewhere else. Where's that somewhere else? Until we define what that somewhere else is, we can't explain this prediction, okay, or this actuality. So at this stage, it would come down to a memorization technique. So a lot of students will take their periodic table as soon as they get it. Remember, it's on the back of the front page. And they would write down your atomic radius trends and metallic character trends. You already knew the metallic character trend, right? Where are all your metals? The left of the periodic table. Where are all your nonmetals? To the right. So we've already explained the left to right trend. We also have the up to down if we look at that staircase. That's also explaining our metallic trend. Okay, so our atomic radius and our metallic character are both in the same system. So at this stage, we could just memorize for the 5 seconds it takes to get the exam, write your people's names on it, and then flip it over, draw on your lines, and be like, there it is. Okay. That said, one of the test questions is, explain the trend as we move left to right on the periodic table. Okay. What we just said is we need to understand something about where the electrons exist to explain that trend. That becomes very tricky. Okay? So we'll move back to chapter 4. And oddly enough, we go into this thing of looking at light. Why are we looking at light? Right? Well, the reason we look to light is that light was what gave us the clues about where our electrons exist. Without understanding some basic concepts of light, we don't know what's going on with our electrons. So, some basic concepts. We've got energy associated with them. All light has a form of energy. We have wavelength, which is the distance from peak to peak. Frequency, the number of times that your peaks appear or repeat within a given distance or a given time frame. And then we also encounter the speed of light, 3 times 10 to the 8th meters per second. Okay. In future chemistry classes, you might be expected to run some calculations with these. At this stage, all we really need to know is those definitions and kind of work from them. Okay. As we look at our light energy, we can actually expand this into something known as our radiant energy spectrum, which shows the full spectrum of all of our possible energies, okay? Which ranges all the way from our very high energy particles, cosmic rays and gamma rays. We've all heard of the gamma rays, right? Okay. There we go, little Bruce Banner. All the way up to our lowest energy light, or lowest energy frequencies. We can go out into the radio frequencies. Okay? And we all know about how dangerous our radio frequencies are, which is why we blast radios. And don't panic about turning into the Hulk. Okay? We don't have a whole lot of energy stored up in those radio waves, but there's enough energy that we can then manipulate and interpret those. Light as we know it is referred to as the visible range of that spectrum. The visible range on us looks like this huge, massive section. Red to blue, I mean, that takes up almost the entire spectrum up there. Except if we look at the scale, very, very tiny range for visible light. Okay. What we've done is interpreted that energy as colors. So we've got pigments in our eyes that will respond to that energy, and we take that response and say, that color is purple. That color is green. But it is our response to that light that's associating now on this color spectrum. Some other things to kind of memorize in there. It might be helpful to know the colors of light within the rainbow spectrum. What are the colors of light? Red, orange, yellow, green, blue, indigo, violet, also known as Roy G. Biv. Okay, great. So you can have that memorized. Okay. But is that really all the light or the colors of light in there? No. No. Remember, it's all colors of light. Those are the arbitrary lines that we decided to drop on this. Okay, we decided that this was best described as red. We've got orange, our yellow, our green. I think that's indigo. And our violet. I missed blue. I was like, that's a really odd space for indigo. Indigo is somewhere in here. There's our blue. Okay. Or Vibgyor, right? Different country. Okay. So Roy G. Biv tends to be an easier name to remember, so we tend to remember that. And that at least gets us our colors in there. The next part that I want you to remember is the energies associated with those. Which one's higher energy, which one's lower energy? Okay. Violet is higher in energy. Okay. I will freely admit it took me forever to remember this, because I look at red, and if we look at the wavelength for red, it's 700. We look at the wavelength for violet, it's 400. I think a bigger number means bigger. Okay, so we think bigger energy. No, they're an inverse relationship. So how do we get that tied down? Okay, well, there's a couple other forms of the electromagnetic spectrum that you are aware of. Okay, when we walk outside into the sunlight, what are we afraid of? Don't tell me clowns. Cancer. Okay, where is cancer potentially coming from? Ultraviolet radiation. Okay, ultra because it is more than violet. So our ultraviolet energy is a higher energy form of our violet light spectrum. Okay? And it is dangerous because ultraviolet light has lots of energy associated with it. Okay? So our violet being closer to the ultraviolet should be the higher energy color. And red will end up being our lower energy color. What's closest to red on our electromagnetic spectrum? Infrared. Okay, when we walk outside, we go, oh, this is stupid infrared light, man, it's way too much, that's going to hurt me. No, we aren't concerned about it. Why not? Lower energy. Okay? So we're looking at those comparisons to come up with some rough ideas on those energy relationships, and that becomes important when we then start to move into our next section, which is referencing atomic line spectrum. Okay? So if we take a prism and shine white light at a prism, what do we end up seeing come out of it? All the rainbow colors. Okay? We can do a similar thing with elements. Okay? We can cause our elements by pumping a bunch of electricity in them, and instead of generating a white light, they generate a colored light. Okay? So we're just putting enough energy in, they spit out a light. And if we take that light and put it through a prism, it will break down into the components that made that color. Okay. So if we saw, say, a green light, we might expect the green range of our visible light spectrum to show up. Maybe a little bit of yellow, maybe a little bit of blue. Okay. If we saw a red light, we might see a whole bunch of the red show up. What we end up seeing instead of this big range of colors, we see lines. Okay? This is kind of odd. Okay? So in this case, we're taking hydrogen, and what we've done is we've excited it with a whole bunch of energy. Okay? When the atoms release that energy back out, they will release it as light. If we then take a look at that colored light as it passes through a prism, it will then spread it out into the individual component colors that made the light that we saw, just like with white light. With white light, we see a continuous spectrum all the way through. When we do this with a hydrogen or any of our elements, we end up not seeing a continuous spectrum. Okay? Not only do we not see a continuous spectrum, we only see individual lines. We don't even see a range. Okay, hydrogen spits out kind of a purpley red color. We don't even see like a whole bunch of red at one end and a whole bunch of purple at the other. Okay, all we see is an individual line for that color, which seems a bit odd. What that's saying is that when we excited the hydrogen, it only emitted very particular energy light. Okay, that's a bit odd. That means what's happening within the atom is that we are causing excitations that only occur at very particular energies. Because if it occurred at all energies, we'd see a full rainbow color. If it occurred at a large section of the red, we'd see the whole red section lit up. Instead, we only see a single line. This is a really odd observation. So what we did as scientists, or rather what Bohr did as a scientist, was took this data and said, well, you know what? This is going to be due to our electrons. Okay? And he theorized that the electrons aren't just this free mass floating around the nucleus. They are located in very particular points, okay, or energies around our nucleus. So for some reason, that projector works really nicely and this one does not. Okay, so let's draw on Bohr's model here. You can see it stand out a little bit better. And what he theorized is that if we took an electron, it can only exist in that energy level. Okay? So what happened is when we excite the sample, or excite our hydrogen by pumping a ton of electric energy into it, we cause that electron to jump energy levels. So instead of being at its nice, happy, lowest energy level, it jumps up to a higher energy level. Okay. What do things at high energy tend to do? Release the energy and come back down to a ground state. Okay. So once that atom is no longer being excited by our electric current, we now have this extremely high energy electron that is now freaking out and saying, I need to get rid of some of this energy. So what it does is it will eject or relax back down to the ground state. We usually show that with a wavy line. But what happened to the energy? I mean, to jump up, we got that energy from the electric current that we dumped into it. What happens to that energy when the electron goes back down to the ground state? It has to go somewhere. It has to be converted out as something. And in this case, it happens to get converted out as light. The energy of that light will be equal to the energy between those two orbitals. Okay? Why is this a big deal? Well, in our previous situation, we just said our electrons were free-floating wherever they wanted, which means they could absorb energy and move to anywhere they wanted. Then they could relax back down to anywhere they wanted, which would then mean what energy should we see? We start at any arbitrary low energy and any arbitrary high energy. We're going to end up with the complete spectrum of all possible energy transitions. We don't have a complete spectrum. We had these lines, very distinct lines. Bohr's theory explains that by saying the electrons can only exist in very particular locations. Those locations have an energy associated with them. We call those particular locations orbits or shells. Okay? This is a pretty massive discovery. Okay? The term that he's used to define this is that our energy levels are quantized. There are distinct steps. The best example to explain this, if we take a look at our orbits, or where our electrons can exist, if they existed as a ramp, continuous energy being anywhere along that line, or along that ramp, I could move the ball to any one of those locations. When I release it, it will release that energy corresponding to that distance, that height, right? If we go through and look at an individual step, where can I place the ball on the steps? Can I place it anywhere on the steps? It can only settle on an individual step. I can't place the ball on this line halfway between the two steps, because then it's not making contact. If we look at the ramp, I can make contact with the ball on the ramp at any level of energy. The steps, I cannot. Quantization, I think I said that right, is like steps. Okay? We have distinct energy levels, or discrete energy levels. The ramp is a continuous spectrum. Okay? We'll pick up there going back to our atomic line spectrum on Thursday. And then we're going to blow your minds even more by looking at orbitals and what they look like. Please, please, please read the section in Chapter 4 on what orbitals are, what they look like, so you have a general idea before we come into class. Yes, it is confusing.